inferential statistics. And I know that some of you have done these things, but I also know that others haven't done it. So we need to be really on the same page. And as I said, this is something I'm really, really fascinated. Why? Well, we've done a little bit of statistics at the beginning of this module, where we said, oh, we want to describe some scientific data. So we learned a little bit about how we can describe data and how we can present data to other people. And that was the topic of descriptive statistics. You remember that? We've done, for example, the mean, median. What was the third one for that? Mean, median, and mode, yeah. And that told us about what is actually the center of, or what is the tendency or measurement of tendency. And I used one of these measurements already when I said, the average for the assessed practical is 82%. That is the mean. It doesn't mean that everybody will get 82%, but, that's sort of measurement of tendency. We also introduced the concept of variability, of variation. And we had particularly variance and standard deviation. We also used concepts like range, like interquartile range, and we also learned how we can show these things when we want to present our data. So this was a measurement of, bless you, measurement of dispersion. Or just simply variability. How variable are our data? And you remember, we looked at that in the context of accuracy and precision. So that is descriptive statistics. And if you like, in descriptive statistics, we use the data to tell a story. This is what we measured. This is how we measured it. This is what we got out of it. This is how our data look like. So we are telling a story. With inferential statistics, it's exactly the other way around. With inferential statistics, the data tell us a story. And everybody likes a story. I love stories. And here are the data, and they tell me something. They tell me a story about the real world, about my environment. So, what on earth does that mean? Well, in inferential statistics, we get to know what the real world looks like. I'll give you an example. A while ago, my sister phoned me. She lives in Germany. And she said, "Dear brother," you know, when she starts with "dear brother," there is something she wants. And she said, "I want to earn money." Good, yeah, fine, great. She said, "I have a business proposal for you. I know your ideas." And she said, "I want to make lab coats." You what? "I want to make personalized lab coats." And you're teaching bioscience students, don't you? So they would use lab coats, wouldn't they? Yeah, okay. Yes, I had no clue where she was going with that. And she said, "Okay, I need your help," she said, "because I need to know how big I should make these lab coats. And I want you basically to sign up for a project where I can flog my personalized lab coats to your BI 308 students." So, okay, fine. Yes. "What do you want me to do?" And she said, "Well, I need you to find out how tall are your bioscience students. Because if I know how tall they are, I know how much material I need to use for my lab coats." And I said to her, "Are you completely nuts or what? Yeah, I've got 260 students. What do you want me to do?" And she said, "Well, measure them." Really? 260 students? Some of them I've never seen in my life because they don't turn up to the lectures. How am I going to do that? So she said, "Can't you just simply use a simple sample?" Oh, okay. So I promised her that I will do a sample so that she can make her lab coats. And that is exactly what I'm going to do with you. All right? Can I have 3 volunteers, please? Who would like to volunteer? Dave. Oh, he's not really a BI 308 student. Okay, no, you stay. Can I ask you, as a volunteer? Right. Okay, good. You step on this thing, on this, yeah? And I just simply measure. Okay. So that is, thank you very much. So that is 183 centimeters. So sample, 183 centimeters. Okay, need somebody else. Lisa, can I borrow you?
I've got heels on.
Oh, you've got heels on? Oh, that's all right. I'm not going to tell my sister. Step on it. Oh, beautiful. Oh, good. Thank you. That is 177 centimeters. Lovely. So 177 centimeters. And you think I can't see you when you look away. Right, okay, good. Okay, can I ask you? Are you happy with that? Be measured. Good. So step on that. Oh, let's do it like that. Okay. Good, got step two. Okay, wonderful, thank you very much. That is... Really? Honestly? Well, that's 158 centimeters. Okay. So now I have a sample. Two female, one male. But he didn't ask about that. And that is my sample. And my hope is that from this sample, I can make a prediction how tall, on average, you all are. So that's a prediction. About the height, of the entire BI308 population. Can somebody please do me an enormous favor? Somebody who has a calculator at hand. Can you please calculate for me what is the average of these here? Thank you. So I just got a first result here. How do we calculate the average? Well, we add them all up and divide by 3. Yeah? And we would get an average of 172.67 centimeters. Is that right?
Yeah.
Brilliant. So this is the average. Now, obviously I can report back to her. My students are on average 172.66 centimeters. There's a slight problem with that, isn't it? Because there's a certain variability in it. Can you get up for a moment, please? No? You don't want to? Okay. Just for a moment, I don't believe that you are 172.66 centimeters.
152.
152? Oh, I don't even have to measure you. So, thank you very much. So, in a way, there is this huge variability in it. But yet, I would assume that this measurement that I just did with the average is nevertheless useful to make this prediction. So my prediction is that the average in the population, and with population I mean you folks, BI308 guys, that the average in the population is around 172.67 centimeters. Now, obviously, we need to be careful with our language. We are talking about average here, average of the sample. of sample. And here we talk about average of population. And people, by convention, have decided if you've got a sample and a population, sample, population, we call the average of the sample, we call that x bar. And the average of the population, everything that has to do with population will be in Greek letters. And the average of the population is called mu. In this case, it doesn't mean micro, it means average of the population. Yeah? Likewise, we have just seen there is a variation in it. The sample has a variation. So we could say variance in the height. And we could, because what was the variance actually? What did the variance tell us? Can you remember? It told us actually how far away on average the samples are from the mean. So what we did was basically, it was, remember, the sum of the individuals minus the mean, bless you. And because it can be in both directions, it can be smaller than the mean or it can be bigger of the mean, we had to square it. Remember? And then we had to divide by something. And for the sample, I told you, if we are ever dealing with a sample, can you remember by what we divided? N minus 1, exactly. And you probably thought, why on earth is it N minus 1? Where's this minus 1 coming from? This is bizarre, isn't it? Well, we can, of course, we can do the same thing for our population. We can say we have the individual, each one of you, minus, in this case, the median of the population, squared. And because, in this case, if I took all of your measurements, all 262 students, I would be able exactly to pinpoint what is the average difference. Yeah? So, in mathematical terms, this would be pretty certain what I'm doing here. And we know that the average is just simply divided by n. That's the variance. So why do I use n minus 1 here? What I'm actually trying to do is, I try with my sample, and that is the whole point of the inferential statistics, with my sample, with the sample statistics, I try to predict the population parameters. Now I'm using weird words here. Sample statistics. A sample statistic is X bar and the standard deviation, which is usually abbreviated with an S. These are, when we talk about a sample, these are called the statistics. And I predict, or I try to predict, the population parameters. The population parameters are the mean and the population standard deviation. That's this sigma thing. So that is the population mean. That's the population standard deviation. Yeah? So when we have a population, we are talking about parameters, and everything is in Greek. If we have a sample, we are talking about the statistics, and everything is in normal letters. Okay? So that is what inferential statistics basically does. It is trying to make a prediction from a small sample, what does the big population look like? Does it make sense to you? Instead of measuring everybody, I just simply take a sample. Makes life much easier for me. Sometimes you have to do samples. I mean, with 260 people here, it would probably take me 3 or 4 hours to measure you all. It's doable. But let's say I want to measure the average size of house mice in Britain because I want to build a trap to catch them and hopefully catch them alive. So I need to make the trap big enough so that the mouse gets in and is safe. I don't want to make them too big because otherwise I would waste material. So how do I know how big I have to make this trap? Well, to be absolutely 100% sure, I would have to catch all the house mice in Britain. So that I know how big I have to make the trap. A circular argument would be total nonsense. If I've caught them already, I would not have to have a trap, right? It would be fairly bonkers. But if I try to catch 5, 10, 100 mice, I could potentially make a prediction how big I have to build the trap. Because I just simply measure the mice, I measure my sample statistics, the average, the mean, the X bar, and I measure my variation, my standard deviation, and from that I can then make an inference out. This is where the inferential statistics comes from. I can make an inference on what the population actually looks like. True? Makes sense. Okay, so far so good. Now we have some measurements here. 183, 170, 758 centimeters. Actually, I'm slightly worried about these measurements. maybe I should repeat that. Because what I have taken is really measurements only here. What about these guys up there? Maybe they are all taller or all, midgets. Tell you what, because I'm so worried that I get a bollocking from my sister by giving her the wrong data, I think I should repeat that. Yeah? You agree? Fantastic. Okay, you too. I need you. Good. But do you know how tall you are? No? Good. Let's keep that on the floor. Yeah, hold that. Okay, thank you. That is 179.
Can you make sure I'm taller than Tom? He said 180.
Tom, don't let go. This is not a competition here. It is, you're actually exactly the same height.
Oh.
I'm so sorry, guys. So I've got 179, and I need somebody. Oh yes, you. Thank you. Oh Jesus. I don't know if the tape measure just about. Thank you. And that is really 185. 185 centimeters. Can somebody please give me the average? X bar is 181. Thank you very much. 181 centimeters. Just a quick question. Everybody who I measured is actually a bioscience student, is that right? BI 308 student. Yeah? We don't have any politics students. Good. Just checking. Because now we have a very strange situation. And I have a massive problem. Can you see that problem that I have? My first sample was 172.67 centimeters. My second sample was 181 centimeters. So I've got 2 X bars. And my ambition is using a sample to make a prediction about a population. Do you see the problem? What can I do? Actually, why is there a difference between the 2 samples? Should there be a difference? Should there be a difference between the samples that I have taken, between the 2 different means? Should there be a difference? Who thinks there should be a difference? Hands up. Who thinks there should be no difference? Who thinks, I wish he would stop now and I could watch Netflix? At least somebody's honest, thank you. There's no reason why there shouldn't be a difference. If we take samples that represent a population, and there is some variability in this population, it is not unreasonable to assume that there are differences. We expect differences. If I had, for example, you guys here, you don't, I might be wrong, and don't worry, don't look so worried, I'm not going to measure you. But you don't look like you are basketball players, are you? You're not very tall, are you? So had I chosen these three young ladies here, I would have gotten a completely different sample mean. This is actually called the fact that I get different sample means. This fact is called sampling error. Sampling error simply means when I pick a sample, I get a certain value. If I pick another sample, I will get a different value, probably. Error in this case, well, error usually means I make a mistake. I'm either dumb or, something didn't work out. But in this case, error doesn't mean that. Error means that every time I do a sampling, there is naturally a difference between the samples. Yeah? Can I avoid sampling error? The answer is no, never. I cannot avoid a sampling error. Sampling error will always happen when I use a sample. So if somebody says, but you made a sampling error, don't fall into depression. Sampling error is absolutely fine. You can't avoid it. Sampling error is, if you like, God-given, or given by the gods of statistics. Can't avoid it. And yet, we want to find out how we can actually predict our population. So what that basically means is, for example, I have sample 1. Thank you. Did anyone ask Siri what it means, or? I want to use sample 1, sample 2, and sample 3 to predict my population mean. But then I'm aware that each of these samples includes potentially, or is different from the other sample, naturally. Yet, hopefully there is a method that allows me to predict the population mean. Very often we are faced with the problem, okay, we have two samples. Do these two samples actually come from the same population, or do they represent the same population, or do they represent two different populations with two different parameters? So what we could say is, as a starting point, we have two samples here. Two samples. And one thing is, they represent the same parameter here, the same population parameter. Or in other words, we could say, for example, S1 and S2 predict a population each where mu1, the average of the first population, is identical to the average of the second population. That is one scenario. And that would be for this one here, where they predict exactly one thing. They are basically from the same population and describe the same population. Or, alternatively, I might have a situation where the two samples describe two different populations. And in this case, the population means would be different. And we can write it like that. Population mean is different. So, in a nutshell, if the two samples predict the same population, we would have this case. If the two samples predict two different populations, we would have this case. Sounds all terribly, terribly esoteric. And probably we can't yet see the implications of that. But I always want to end on a cliffhanger. So I tell you what this actually means and how you can apply it in the next session. Okay? Don't run away. You get your questionnaires. Where are the questionnaires?